All right, guys, I want to get through a transformation of the tangent function with you. I think those are one of the harder things to kind of transform. Um, then we'll talk about the secant and cosecant and how you develop those parent functions for them. But the idea is when you get to a secant or cosecant and you want to transform it, you really don't transform it. You transform the sine or the cosine that gets paired with it, and then kind of do what we're going to do here in a little bit with it. Does that kind of make sense? So you never deliberately will graph a cosecant function. Okay, you will graph the sine function. Okay, whether it's got transformations or not, and then kind of go through a pattern type procedure to get what then the cosecant would look like. Okay, so we'll get to that, talk about that in detail here, hopefully by the end of the period. But I want to do the tangent function. Remember the tangent function, the parent function. You have an asymptote at x equals negative pi over 2, and you have one at x equals pi over 2. Those are your initial parent function asymptotes. You have the point 0, 0. Okay, so halfway in between, you cross the x-axis, and that's something to keep in mind as we stretch these things horizontally, as we move them left and right. Between two asymptotes, any two asymptotes that are consecutive, you will always cross halfway in between them. Does that make sense? You'll always have an x-intercept halfway in between them. Okay. Now that creates this interval right here between 0 and pi over 2. And halfway inside that interval, you reach a maximum, or not a maximum, but you reach a height of 1. Okay. Now, that relationship should exist when we stretch these things, move them left and right. Inside that interval, halfway in between, you will reach a height of 1. Okay. And then if we have negative pi over 4, we'll have at negative 1. Okay. And this is because that point at 1 is because on the unit circle at pi over 4 radians, you have an x value of radical 2 over 2, you have a y value of radical 2 over 2, and when you divide those, that's what tangent is, it's y over x, you get 1, right? Okay. At negative pi over 4, that's the kind of the halfway point in the fourth quadrant. You still have radical 2 over 2 as your x's and y's, but in the fourth quadrant, your y is negative. So you got negative radical 2 over 2 divided by radical 2 over 2, and it gives you negative 1 as a quotient. Okay. And then, obviously, if we graph the tangent function, we see that it does exist in those 3 points, or those 3 points exist on it, and it is happening between those two asymptotes, right? And then these other ones are just developed by cutting and pasting those relationships. Okay, is that all right? So that's what we did. We talked a little bit about that on Thursday and Friday of last week. I want to take one of these, or this graph, and I want to transform it. So in order to do this, guys, so that it all gets on film here, I'm going to cut and paste this into maybe PowerPoint. Maybe. It's always a really, really good idea when you're graphing transformations to have the parent function right next to you as you're doing this. So Control V, there we go. All right, so I'll have that thing to compare my graph with. And we are going to, once we graph this, we'll go back to GeoGebra and make sure that it's all done correctly and what we've developed mimics the actual graph. And I think that's something to kind of do as you guys are doing these things, maybe by hand. Always go back, use technology, because that's going to help you kind of justify whether you've done things correct or not. So what I want to graph is y equals, let's go tangent of 1/2 x plus pi over 6. Okay. Now, in graphing that, we'll never really graph that one. Okay. Because I guess written this way, because that 1/2, right? We don't like that coefficient to be different than 1. Because when it's different than 1, it tells us that this transformation, this horizontal movement is not accurate. Okay. So what we want to do is we want to do a little bit of work with that and factor that 1/2 out. So if I factor that 1/2 out, we get y is equal to tangent. I'm going to write it this way, 1/2. Okay. Now x plus, now if I factor a half out, factoring is the same thing as dividing, right? So divide by a half, that's the same thing as multiplying by what? 2. So let's multiply that pi over 6 by 2. And what do you get when you multiply pi over 6 by 2? Pi over 3. Okay? And that seems to be, just in the past, the trickiest thing for students to do and to figure out. And if you know that you're going to struggle with that, before you go on to anything else, before you go on to any graphing, if I factored, can I distribute to undo it? And if I multiply that through, don't I get 1/2 times x, give me 1/2 x. 1/2 times pi over 3 gives me pi over 6, which is exactly what I needed, right? So I know that tangent equals 1/2 x plus pi over 3 is what we're going to try to deal with here. Okay? Y equals 1/2, or tangent. Just trying to give myself a little room here so when we graph it, we don't have a lot of things overlapping. All right. So that's what we're going to graph, okay? Now, if you remember, that's your b value right there, right? And your period for the tangent function is pi over that b value, pi over b. Well, that's pi over 1/2. What's pi divided by 1/2 going to give me? 2 pi. So my period is 2 pi for this particular function. Right. Now, think about how that kind of sets things up for us. If this was our parent function and it had a period of pi, now we're going to have a period that's twice as big, right? Does that make sense? Okay. So where would be my starting points and ending points for those asymptotes? If it's going to be twice as big, wouldn't my first asymptote be over here at 1 pi? And then over here would be at good. Okay. Now I think it's a good idea to go through, and because obviously we're going to have asymptotes there, we just got to be careful. Don't draw these, when you draw these asymptotes, kind of make them light, because they're going to get moved, aren't they? Our transformation has to happen left or right here because that pi over 3. So I just, kind of what we did in the last class, and I do this every single time that I have to conduct one of these transformations. I always graph, no matter what trig ratio I'm dealing with, sine, cosine, tangent, secant, cosecant, whatever, I just graph it without the horizontal transformation first. Okay? But I do it really light, because then once I do it really light, I then say, okay, now that I have that image, can I then move every part of that image left or right, however far I need to? Okay? So I'm going to graph that blue one first. Okay? I'm going to graph everything except for the left or right movement. So, that being said, okay, this should be a lot easier to graph now, because it should follow the same symmetries that this parent function had. All right? So halfway between your asymptotes, you have an x-intercept. So that would mimic to that point right there, right? Okay. Now, between that point in either asymptote, you reached a height of 1, right? So halfway in between, I should reach a height. I will put 1 here. I should reach a height of 1. And then halfway in between that interval, we reached a height of -1, so I should get the same thing. Reach a height of -1. Okay? So those are the key points in asymptotes for tangent 1/2x. Okay? Now, it's probably a good idea to at least have, that's pi over 2. This would be negative pi over 2, right? Okay. Now what I want to do, guys, is now I want to deal with that movement. Okay. So everything is going to get shifted left pi over 3 units, right? So in order to do that, I should probably have my x-axis labeled in thirds. Okay. If it was 6, I'd try to label it in 6. If it was 12, I'd try to label it in 12. Or 4s, I'd label it in 4s. Does that make sense? So whatever that denominator is, I'm going to try to label my x-axis that way. So it's pretty easy when I've got this to 0 to pi. Just break it up into thirds. So there'd be pi over 3. And that would be 2 pi over 3. Be negative pi over 3. Negative 2 pi over 3. Now I do need, because everything's getting shifted left, I do need this negative 4 pi over 3 over here as well. Okay. Now here's the thing, and you're gonna find this out, that even though that we put our intervals in terms of pi over 3, there's still going to be maybe some fractions here that we use that don't necessarily show up. Okay. I think we end up having some pi over 6s that we need for essentially that point right there and that one there. Okay. But what I'm going to do first is move my asymptotes. I think that's the easiest thing to do. So this asymptote here is going to become, I'm just make it solid now. It's going to move to the left pi over 3 units. So it becomes that asymptote. And this purple one here is going to move over to there. Is that all right with everybody? So we now have those asymptotes. Now, if those are our asymptotes, let's see if we can move these points the same way. And it's probably easiest to at least move this point first, because it should go pi over 3 units to the left, right? So it should go right there. That makes sense to everyone? Okay. Now, here's where you've got some options on how I move these other 2 points. You can either say that I'll do it this way. You know that because in the parent function, halfway in between that interval, in the parent function, you reached your 1, right? So now halfway in between this interval here, we could reach our height of 1. But we got to figure out what that halfway point is. Does that make sense? So I could say, halfway, just using our, if I go negative pi over 3 minus, what is it? 2 pi over 3. Oh, minus 2 pi over 3. So I'm just trying to figure out what that distance is there. And we should know that that's pi already, but just doing the math here, we get negative 3 pi over 3, but distance should be positive, so I take the absolute value. So we get negative pi, but now, or positive pi, sorry. So that's that blue distance right there is pi. Does that make sense, everybody? Which should make sense because isn't your period 2 pi? And we know that should be halfway, okay? So if you want to do that math, you can. You don't need to if you knew what your period was. But now I'm going to find halfway of that, so it'd be pi over 2, correct? So pi over 2 would be the distance that is halfway from this point to that asymptote. But this point starts at negative pi over 3, right? So what I do is I take negative pi over 3, add to it pi over 2, okay? And that's going to be, what, negative 3 pi over 6 plus, negative 2 pi. Negative 2 pi over 6 plus 3 pi over 6, right? And that gives me pi over 6. So that gave me the location of the halfway point, and it's pi over 6. Okay? Or you can do it this way. You can say this currently had a pi over 2 x value, right? Remove pi over 3 from it. Okay? We'll move it to the left, right? So then this would be, again, 3 pi over 6 minus then, this becomes 2 pi over 6. So it tells you to move it to pi over 6. Does that make sense, everybody? Okay? You just need to figure out a way that you can accurately move this point to there. Okay? Which, if you think about it, we did not have, when I labeled my x-axis in terms of thirds, that pi over 6 was not there, right? Does that make sense, everyone? Okay. So it is going to go to pi over 6, comma 1. And I think it's a good idea, especially these points, to label them, what you found them, because on a test or a quiz, if you have the correct labeling, but maybe it's a little bit inaccurate in its positioning, I'll give you points, I'll give you full credit as long as you have the ordered pair. Does that make sense? Because I understand how difficult it is to gauge distances on the x-axis right now in terms of fractions. But as long as you got those ordered pairs, I can tell that you did know what you're trying to do here. Okay. If I start at negative pi over 2 as an x value, that needs to be moved to the left pi over 3 units as well. So again, that's negative 3 pi over 6 minus 2 pi over 6. So that should go to negative 5 pi over 6. So we got to find negative 5 pi over 6 over here. And it's actually going to be right there. And that's the halfway mark between my x-intercept and my first asymptote over here, right? And that order pair should be negative 5 pi over 6, comma negative 1. Okay? Guys, I'm fairly confident that you guys are going to be able to find that intercept and say, okay, well, that distance to my asymptote needs to be cut in half, and I find my y value there. Okay? And same thing here. That distance gets cut in half, and I go down to find my y value, or my ordered pair. But what I need to know is that you're able to not only cut that distance at half and find it location-wise, but actually be able to identify it and label it. Okay? But now that I have those, I'm going to take a smooth curve and draw it through those 3 points. And that's kind of ugly right now, but that would be your tangent function. Okay? Your 1/2 x plus pi over 3. Now, I'm going to go back to GeoGebra and just see if indeed what we've done can be mimicked by the computer, because the computer does a much better job of graphing than we do, right? Okay. So I'm going to graph, I'm just going to graph tangent of 1/2 x. It was pi over 6 is what we started with, okay? And I don't think that did what I wanted it to do. I think I put an extra parenthesis in there somewhere. Nope, I need to get the 6 in. Pi over 6. There we go. All right, so that's the graph that we should have, okay? We first found that we had an asymptote at 2 pi over 3 and one at negative 4 pi over 3, right? So let's plot those. X equals 2 pi over 3. X equals negative 4 pi over 3. Do those look accurate like asymptotes? Yeah. Okay. We also found that we had an x-intercept at negative pi over 3, 0. So let's see if that point is on there. Negative pi over 3, 0. That point is there. We also had, the point that is up here at 1 where my cursor is. That should have been, I think we had pi over 6, comma 1. So that falls on the curve. And we also had negative 5 pi over 6, comma, negative 1. And we're seeing that that did fall on that as well. Okay? So all that work, guys, is actually getting those ordered pairs, now that they've already got pi multiplied through them, but getting those ordered pairs in the right spots. Okay? Is that something we can kind of do? I know it's a long, tedious, kind of pain in the butt process, but if we force ourselves to work with that, I think there's some things. Obviously, we learn how to graph the tangent function, which is ultimately the overall goal. But a byproduct of that is you get pretty good at dealing with fractions, multiplying, adding, subtracting, that kind of stuff, which is very useful. And you're gonna find out in the next couple of days the trig that we do. Obviously, we're trying to learn trigonometry, but a huge byproduct of that is that we get really, 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 really good at our algebra. Okay, so that's the tangent function. You can transform it any way that you need to using those steps. Okay, whether it be a 1/2 that we factored out, or a 2, or 2/3, whatever, the process is going to be the same. Okay, let's deal with the secant and the cosecant briefly. I want to graph y equals, let's do secant first. Secant of x, okay? And here's the thing, okay? I don't really want to graph the secant of x, okay? At least in the process of getting this graph, we're not really going to focus a whole lot on the secant, okay? We're going to look at its reciprocal. What is its reciprocal? Cosine. We already know how to graph that thing pretty well, don't we? Okay. And what I'm about to show you is the exact same thing that you would do. Let's say you wanted to graph y equals 1/2 secant of, 2x plus pi. You would never deliberately graph that. What you would do is you would graph this first. 1/2 cosine of 2x plus pi. Does that make sense? You're always going to graph that, the reciprocal function first. And then once that is done, you are 3/4 of the way home to graphing the 1/2 secant of 2x plus pi function. Okay? By just mimicking what we're going to do over here. We know that the cosine function should have a point at 0, 1. It should have a point at 2 pi, comma 1. It should have a point at pi negative 1. Pi over 2, comma 0, and 3 pi over 2, comma 0, right? Those are the parent function points that we have kind of memorized. and we're going to draw a smooth curve through there, and we get that cosine function, right? Okay. And like I said, if you ever want to transform the secant, you would actually graph the transform cosine of that. Okay, maybe I'll give you an example here in a little bit. Now what we're going to do is we're going to find some critical points on this thing. One of the first things I would do is go look at that point, that point, that one, and that one, because they are a radian measurement, comma, or cosine value, right, from the unit circle. Okay, so that y value is the x value off the unit circle. Well, when I graph the secant, it's still the same -3 pi over 2 radians, but now it's not the cosine from the unit circle, it's the reciprocal of it from the unit circle, right? So that 0, its reciprocal, would look like that, wouldn't it? What's a number divided by 0? Undefined. So right here at -3 pi over 2, you have an asymptote. Because you have an undefined value. You have division by 0 there for the secant. What about right here at -pi over 2? Is that going to be undefined as well? What about pi over 2? 3 pi over 2. Okay? You see that your asymptotes occur at pi over 2 plus pi k, where k is an integer. And that will mimic, that'll get you all those additional asymptotes. Okay? So that's nice. Okay? And once we have that, we're pretty much done. Okay? Because we're only going to then focus on the maximums that occur, maximums or minimums that occur in between two asymptotes. So look at between these two asymptotes, there's a minimum point, right? Now that y, that ordered pair is -pi comma -1, right? But what's the reciprocal of -1? -1. So on the secant function, that point should exist. That point is going to be on there. It's shared by both curves. Does that make sense? Okay. Let's come to this point here at 0, 1. What's the reciprocal of that y value? 1. So that should exist on the secant. And then that pattern just repeats. Okay, so all of those maximum minimums of the cosine function actually become maximums or minimums, respectively, for the secant. Okay, now it'll be a maximum or minimum in that interval, inside those asymptotes. Once you have those, all you do is you start at a point, one of those maximums or minimums, and then you move left and right towards your asymptotes. I can't go down, right? I can't cross the x-axis again. So I'm going to move up. Now here, I'm going to move to the left towards that asymptote. And then I'll move towards that asymptote. We'll see how the asymptotes in that point get us our curve. And now our period would still be, what was the cosines period? 2 pi, right? Do you see if the secant's period is still 2 pi? Okay. Because, if I look at the curve in between that purple region, it's going to repeat itself. Wow. I'm going to take a couple minutes I've got to finish this up when you guys leave. But we'll definitely pick up tomorrow with introducing the cosecant and then talk about the cotangent. All right, so finishing this off, guys, you got
this distance here is 2 pi, just like the period of the cosine, because if you see, obviously that curve and that curve, then they start to repeat. This blue one up here becomes this one again, and then we'll get to 5 pi over 2, and we'll get this one down here to repeat itself there. So that thing is going to have the same period um, as the cosine. Now, you would do the same thing with the secant function. So if I'm looking at the secant function, or sorry, the cosecant function, let's say I wanted to graph y equals cosecant of x. Well, I really graph y equals sine of x first, because that's a little bit easier to do. Now I'm not going to spend time in finding those 5 points. I'll just go sine of x. Gives me those. Okay, so now the same idea. Where I have my x-intercepts, you're going to have your asymptotes. Okay, so that's a series of asymptotes. You can keep going as far as you want to. But then you're going to also have, at those kind of maximum minimum points inside those intervals, you'll have negative pi over 2 comma negative 1 as a point on your cosecant. You'll have pi over 2 comma 1 as a point on your cosecant, and then 3 pi over 2 comma negative 1. So it's still those maximum minimums. Then you can graph from that point to this asymptote, and from that point to this asymptote, and eventually you'll find out that you do trace out that curve there. Okay, so the whole idea here is that we recognize that the sine function or the cosine function actually helps us get the secant or cosecant. And you recognize here again that the period from negative pi to pi, the period is still 2 pi. Now, what was I talking about when class started about, maybe graphing y equals 1/2 secant of maybe, I don't know, 2x plus pi over 6 or something like that. All right, well, I'm never really going to graph that. And try to find those ordered pairs. That's going to be hard. So what we'll do is understand the reciprocal concept, and we're actually going to graph this instead. All right, so I'll graph that reciprocal 1/2 cosine of 2x plus pi over 6. We'll graph that, okay? And then we see at these x-intercepts, and obviously as we graph that, we would have these ordered pairs, what those x-intercepts values are, okay? But whatever they may be, we will then have asymptotes. And let's see, let me zoom in. Well, let's just do a little bit of work here. See what that, I want to find out what that ordered pair is, or what that x value is. So I would take the 2 out, so 1/2 cosine 2x. Dividing by 2 is the same thing as multiplying by um, 1/2, so I should get pi over 12 here. So this thing here, my period, should be 2 pi over that, so 2 pi over 2 becomes just pi, so my period is pi, and that is what we're seeing kind of from there to there is pi. So in the normal cosine function, I start, let's look at the parent function. I start here at 0, I finish at 2 pi. So on this one, when my period is just pi, that should be pi. This should be pi over 2. This should be pi over 4, and that's okay. So pi over 4. So uh, 3 pi over 4. All right, so that's getting me essentially to figure out what that distance there is, and now that would be this point here, which would have been moved pi over 12 units. So I'm just trying to figure out what this asymptote would be, and it should be at, it would normally be at pi over 4, but it's now been moved to the left pi over 12 units, so I should have x equals Pi over 4 would be the normal asymptote, but now we've moved it to the left. Pi over 2, sorry, pi over 12 units, so it gives me there. Okay, so there's one asymptote. And then we can take that asymptote. Let's see how I did that. Okay, we can take that line G and add to it my period. Not my period, but well, I'm not going to get into that. It'd be too much extra work here. But we can find those other asymptotes, what I'm trying to get at. But you see at that asymptote, we can find that location. We can find that one's location, and we keep doing that throughout the entire curve. And if you kind of just visualize the asymptotes being here at these x-intercepts, and actually I can ask it to do this. Get those asymptotes. There's one. There should be one there. So now if I put in let's go x equals the x value of a, go x equals x value of b. So we get those asymptotes. But the whole purpose here is to show you that now if I've found those asymptotes, I've got these maximums and minimums here. If my overall goal was to graph, I've deleted it, but see if I can recall what it was. It was y equals, I think it was 1/2 secant of 2x plus pi over 6. If I graph 1/2 cosine of that stuff, I should have enough information using this red curve and those asymptotes to actually get 1/2 secant 2x plus pi over 6. You do see that blue curve then does fall inside those asymptotes that were created by the cosine, and it does fall along those maximums and minimums. It doesn't incorporate those values into the blue curves as well. So that's kind of what I'm trying to hopefully you guys see here. You already know how to graph cosines and sines and move them left, right, up, down, stretch them, that kind of stuff. Now it's just this one extra step to graph the reciprocals of graphing the sine, cosine, and what other transformations are, but then find their x-intercepts, put in asymptotes, and then draw these little curves in inside those asymptotes. Hopefully that helps. Hopefully that makes sense. But I think that's the quickest way to graph these things instead of trying to reference the unit circle and say, okay, create a t-chart or something like that to graph all these x and y values that are associated with this curve.